In our last video, we saw how the Darcy-Weisbach equation gave us a powerful way to predict pressure loss from friction in a long, straight pipe. It was elegant, predictable, and worked beautifully, but as soon as we introduce the real world, that beautiful simplicity breaks. Real-world piping systems are full of fittings, pens to change direction, valves to control flow, and junctions to split it. To the fluid, each of these is a violent obstacle course. When the flow hits a bend, it can't turn perfectly. It slams into the outer wall, separates from the inner wall, and tumbles into itself. This creates a chaotic, swirling mess of eddies and turbulence. These chaotic swirls can be best described as tiny energy vampires. They suck the kinetic energy out of the main flow and convert it into useless heat. This results in a significant drop in pressure that has nothing to do with simple wall friction. Early engineers in the 19th and early 20th centuries knew this was happening. They could measure it, but they faced a huge problem. How do you create a simple formula for something so incredibly complex and chaotic? One of the first clever ideas was the equivalent length method. The thinking was this elbow causes the same pressure drop as, say, an extra 30 feet of straight pipe. So for our calculations, let's just pretend our pipe is 30 feet longer. This was intuitive and better than nothing, but it was clunky. The equivalent length for a valve would be different for water than for oil, and it would even change slightly depending on how fast the flow was moving. It wasn't a universal solution. The real breakthrough came with a more elegant idea inspired by the Darcy-Weisbach equation itself. Engineers decided, instead of a clumsy extra length, let's create a single clean dimensionless number that represents how chaotic or resistant a fitting is. They call this the resistance coefficient, or as we know it today, the K factor. The formula they created was beautiful in its symmetry. It used the same kinetic energy term, rho u squared by 2. This meant you could now calculate your total pressure loss in a system with one simple additive approach. Total loss would be equal to friction loss plus sum of all K factor losses. But where did the values for K come from? They couldn't just be derived from pure theory. The flow was too chaotic. So they were built from pure, hard-won, empirical data. Companies, universities set up meticulous lab experiments. They would build a pipeline, measure the pressure drop, and insert a specific valve and measure the new, higher pressure drop. The difference was the loss due to that valve. They did this hundreds, even thousands of times for every conceivable fitting. 45-degree bends, 90-degree bends, gate valves, globe valves, etc. This massive amount of experimental data was compiled into tables. The most famous of these is the Crane Technical Paper number 410, Flow of Fluids Through Valves, Fittings, and Pipe. First published in 1942, it became the Bible, quote-unquote, for piping engineers and is still used today. And this brings us full circle to what we are doing today. K factor is a brilliant empirical approximation, a single number that represents the result of all that chaos. With CFD, we have a tool so powerful that we don't need the approximation. We can simulate the chaos itself. We can see the flow separation, the swirling eddies, and the K factor simply represents with a number. So let's get started. Okay, let's create our geometry using FreeCAD. So I'll just create the empty file right here and let's go to Sketcher. We'll create a new sketch. We'll call it the XY plane and I'll just toggle the grid on as well. Notice that I have Blender navigation system here. This is what works for me, but it's essential for you to go through what navigation system works for you best. So I'll just select this polyline. Let's start at 0, 0. We'll go a certain distance and a certain distance to the bottom and hit escape. Let's create a fillet between these two, simulating the bend in our pipe. Now we can start giving the dimensions. This is somewhere around 30. So this is the radius of our bend. Next we have the constant horizontal distance. This is somewhere around 200. And finally we have vertical distance. This is somewhere around 400. So this is the first skeletal outline of what the path my pipe is going to take around its center line. So let's just hit close. We'll create a new sketch, this time in the YZ plane. So in my YZ plane, I'll select the circle, and at the same point 0, 0, I'll just make a circle of 20 mm diameter, and I'll just hit close. So we essentially have the pipe and we have the circle which can be used to extrude along this particular path. Now let's go to the part design. Let's create a new part. So I'll just move these two sketches inside my body, and I will select both of these. I'll select both of these to select creating my pipe. Notice how I selected the sketch 001. This is my circle, and second I selected the path. So first you need to select the major body which is going to get extruded, and then the path. That's how it works, otherwise you'll end up with the error. Now that we have this particular body, we also need to export this body as inlet and outlet. So the first thing that I will do is I will go to part. Yep. So once I have my body selected, I'll go back to part. I'll go to part, I'll create a copy, create a simple copy. So once I have this body 001, I will essentially, select one of the faces here, this face, ensure everything else is not visible, just your body is visible. So by selecting this, I will go to part, I'll say create a copy, create shape element copy. Now this can be my inlet. Let's hide my inlet. There we go. So I'll go to part and create a copy. So let's call this outlet, and I'll hit OK. Let's go back to body. Now by holding the control key, okay, let's do one thing. We will box selection, we will select all of these. I'll just zoom in, unselect this, and unselect this. So all of these are selected. Go to part, primitive, create a copy, shape copy. So now to export, we'll just select the body, go to file, go to export. Now let's call this wall.stl. I'll just hit save. Now let's check what this wall looks like. So this pretty much looks like what we designed it. So we have, good resolution of triangles here, and we have made our wall object. The same things we will do for our inlet and outlet. So we have exported the inlet as well as the outlet. If you want to take a look at this, this is my outlet. Not the best, but we essentially need the outlet shape, not the inside triangles here. And similarly, we have our inlet. Same thing, same type of triangles, but serviceable, we will just work with it. So that's how we create the geometry. Now let's move to creating the mesh. So with respect to the ksetup files, not much will change because the same boundaries is what we are using in this particular case. We essentially have taken the pipe geometry, we have put that inside the geometry folder. Other than that, the major change that is occurring is just in blockMesh text. So in blockMesh text, we are just changing the bounds here so that our body can be captured better. And at the same time, the changes that are occurring is in snappyHexMesh and in surface feature dict. So notice how in the surface features dict, we are only interested in the inlet and outlet because these are the essential curved or the boundaries that we are really interested in capturing better. And the included angle is at 120. This just helps capture. And in snappyHexMesh, we have just introduced the inlet, outlet, and walls. One of the biggest sort of contributing factors towards better mesh is the resolve feature angle. This is set at 80. I will explain in just a bit what happens if this changes, and you will see the impact of that. But the essential sort of controls that we are trying to use is 2 levels of feature refinement and 3 levels of surface refinement on our base mesh that we have created here. And we'll just go through what this looks like at the end of it all. We're just creating 3 layers here, and this corresponds to what my Y plus should be for the particular turbulence model that we're trying to use as well. So let's get started with the procedure. So now that it is done, let's take a look at my mesh here. So around my inlet, I can see the mesh has been made. It looks something like this. Let's measure what this looks like. So 0.0015, somewhere around there, and 0.0018, somewhere around there, 0.0015, 0015. So this is precisely what we wanted in essence for our first cell layer height. Now, since the diameter itself is so low, and for my particular case, the pipe itself, has higher velocity of fluid coming in at 0.5 meters per second, this should work. Let's also do one other thing here. Let's take a slice the Z normal. And now let's take a look here. Okay, so this is where the issue lies as well. You will see that the layering is not done appropriately in this region. There we go. So you will see that the layering has missed out on this point and this point, where exactly is what we want the layers to be made clearly well. So we'll just go back to our meshing process and understand how to tackle this. Okay, so we are able to get the 3 layers that we want now. The essential changes that we've made here is we've done 4 levels of refinement on both our features and on our surfaces. And on top of that, I've just changed the feature angle to 90, slip feature angle to 60, and I've increased the first layer thickness here. So let's just take a look at what our mesh looks like. Okay, so this is my pipe. Let's take a look at the inlet. So this is my inlet. Let's just measure the first layer thickness. So according to this, the length is somewhere around 0.00115905. For Y plus equal to 30, we would see that it is somewhere around 1 mm. So this is higher than that. We can expect the Y plus to be greater than 30, hopefully. Let's take a look at that as well. And let's measure the outlet just for, yeah, it is pretty much the same. And towards the end of it, let's also take the slice in Z normal. So let me just crinkle as well, and let's do camera parallel. So we can see that now the mesh looks, much more uniform across the board. Even though in the center line, we can see that the cell size is a little higher. That's fine. We expect more turbulence to come around these walls and move away from the walls and then just slosh around somewhere around this region. So we'll just run the simulation and understand what this looks like with the results. So after 5 different iterations, we essentially arrive at one point here where we have acceptable results. Let me just show what that looks like. So first thing we will do is we will look at the result itself. So let me just open the inlet patch. I'll just go closer to it and, essentially rescale the data to the range. If I go to information, you will see the pressure is minimum maximum somewhere around 152.5 to 154.23 pascals. Now, if you want to be accurate about it, you could be looking at the average pressure data. So if you want to do the area average, because essentially this is, a patch which has cells and have their own areas. Each patch will have its own pressure value, etc. So if you want to do that, you could just open this data in a spreadsheet view and just do the cell data. Now what we would want to do is control space and just do cell size, hit enter, hit apply. So with the cell size, we will get the area and we will get the pressure values. What we have done is export this data in the spreadsheet. So I'll just show what that data looks like. Here what we've done is the data that we get for pressure and the data that we get for the area, both of these have been multiplied. Essentially the summation of pressure times area divided by summation of area. So this right here is the summation of pressure times area, and towards the end we have got the sum of our area, and this divided by this multiplied by 1000 because this is your kinematic pressure multiplied by density. So the pressure that we are working with, or the essential drop of pressure, would be 153.34, somewhere around there. We could round it off to 153.35 perhaps. So with these results in mind, let's now take a look at what our pressure drop looks like when we compare it with the theoretical result and what is the error that we are working with.